Next topic, two-level logic relations. Next topic, two-level logic relations. The two levels are two stages, both are same. From the input to output, you are having two stages or two levels. Okay. For the time being, I am considering AND gates, OR gates, NAND gates, NOR gates. For the time being, I am considering AND gate, OR gate, NAND gate, NOR gate. Okay. In the exam, he may give with any type of gate. Like he may include XOR gate, XNOR gate also. Okay. Here I want to give some conclusions. That's why I have considered these four gates: AND, OR, NAND, NOR. Okay. So from the input to output, we are having two stages. Okay. At one stage, I will consider logic gates are of one type, and another stage I will consider logic gates are of other type, like that. So here repetition is allowed. Here I am considering four types of gates. So total you will get 16 combinations. So first one is AND. Just observe, from the input to output we are having two stages. See, at the first stage we are having AND gate, AND gate. Okay, the output of these AND gates we are giving as input for this particular AND gate, right? So that means from input to output we are having two stages. Two stages or two levels, both are same. Okay, here I have considered first stage is AND, second stage is also AND. Okay, later I will consider first stage is AND only. Next I will consider in the second stage OR. Next one NAND. Next one NOR, like that. Okay, now what is the output? Here output of this AND gate is A and B, AB. Here the output of this AND gate is CD. Okay, so output of this AND gate will be Y equal to AB and CD. This one you can write it as ABCD. Y equal to ABCD. Okay, see here we are having two stages. Okay, with the help of three gates we are getting ABCD. Okay, actually if you want ABCD, we can directly implement with the help of single gate also. With the help of single logic gate, that is 4 input AND gate. With the help of 4 input AND gate, directly we can get this particular function. So whatever we are having, this entire circuit diagram, we can replace with single gate. Okay, if we are able to replace like this, then whatever the function we got from the two-level logic relation, we can call this particular function as degenerative form. You can write down, make a note. If the output of two-level logic relation can be implemented by using single logic gate, then it is said to be degenerative form. Whatever the function we are getting from the two-level logic relation output, okay, if we are able to implement with the help of single gate, then we are calling it as degenerative. Here degenerative means what? Here I am using 3 gates. Okay, whatever the circuit diagram I am having, okay, I am just replacing the entire circuit diagram with the help of single gate. But here I am having more number of inputs. Okay, but we can replace with the single gate. Okay, that is the meaning of degenerative form. It is degenerating to a single gate. See, for each category we will be having 4 types. Like here I have considered first stage AND gate, right? So in the second stage, first case I have considered AND, second case OR, third case NAND, fourth case NOR. Okay, you no need to draw the circuit diagram for each case. Draw circuit diagram for first time. Okay, here I got AB and CD as the outputs. Okay, now in the place of AND gate, assume OR gate is there. What is the output? Directly you can write. Second one, AND OR. Here output will be Y equal to, see, at the first stage, here we got AB, CD as the outputs. Okay, in the second stage, in the place of AND gate, assume OR gate. Here output is AB plus CD. Correct. Y equal to AB plus CD. Here if you observe, I am having product terms sum together. This means SOP form, sum of products. Here I am having 2 product terms sum together. That means SOP form. Okay, next third one, AND NAND. Here first stage I am getting AB and CD. Okay, in the second stage, in the place of AND, treat NAND gate. Then here we will get Y equal to AB and CD whole bar. See here in the place of AND gate, assume NAND gate. X, Y whole bar. Right? X is AB, Y is CD. Like that you can assume. Okay. Now this one we can write it as ABCD bar. This is not canonical SOP. Here for the time being we have considered, see here, AB I have given, CD I have given. Okay. Here it is a 4 variable function. In each in each product term, number of literals is less than the number of variables. See here, see first case what I got, AB and CD, that is nothing but ABCD. Here also I have written AB is there, CD is there, I have considered. Even if you apply De Morgan's law, what you will get here, A bar plus B bar plus C bar plus D bar, that one you can rewrite once again like this. Okay, so see here we got ABCD, that means with the help of single logic gate we have generated. This is degenerative form. Similarly here, if you are having 4 input NAND gate, we can generate this particular function directly, right? So this is also degenerative form. Degenerative form. Fourth one is AND NOR. Here I am getting ABCD in the place of AND gate, consider NOR gate. Here you will get AB plus CD whole bar. AB plus CD whole bar. Here I am getting ABCD in the place of AND gate, consider NOR gate. NOR gate means what? A plus B whole bar format. Okay, AB plus CD whole bar. Now just observe here, AB plus CD is nothing but SOP and complement of it is nothing but complement of SOP. Complement of SOP. Okay, here we have considered AND gate first stage, second stage AND gate one case, in other case OR gate, NAND gate, NOR gate, like that. Okay, so like that for each category draw the circuit diagram for one time starting. Suppose next I will consider OR gate in the first stage. Draw circuit diagram for one case. Okay, after that just whatever the outputs here you are getting, consider those outputs in the place of second stage gate, consider other gate, like that. Like that, try to find out the outputs and represent whatever the form it is. Next one is OR AND. Okay, in the first stage I have considered OR gates, in the second stage I have considered AND gate. Okay, here I am getting A plus B, here C plus D. Okay, these two terms product. Okay, y equal to A plus B and C plus D. Now just observe, I am having two sum terms which are product together, that means POS form. Okay, like that you try to find out for remaining cases. Okay, see, draw circuit diagram for one case and for remaining 3 cases. Okay, consider whatever the outputs here you are getting. Okay, as input for other stage. Okay, in the place of AND gate, treat OR gate. Next NAND, next NOR, like that. Okay, these 3 cases easy people can solve. Okay, and next NAND and NAND OR, NAND, NAND, NAND NOR. W students solve for these 4 categories. EC students try for these 3. W students try for these 4. Draw circuit diagram for this category and then consider the circuit diagram in the place of second stage AND gate, consider OR gate, next NAND, next NOR, like that. Next last one is NOR AND, NOR OR, NOR NAND, NOR NOR. Instrumentation and CS students try for these 4 cases. Draw circuit diagram for 13 NOR AND. Okay, after that you analyze for these 3 cases. ECE students try for these 3 cases. WE students try for these 4 cases. Instrumentation and CS students try for these 4 cases. Put the heading degenerative forms. Whatever the degenerative forms you got. See, total we have considered 16 forms. Okay, 16 functions, 2-level logic relations. From that, whatever the degenerative forms you got, tell me. Yeah, first one is and or will give degenerative, and or NOR also will give degenerative. You will get 4 more combinations. Yeah, NAND NOR, correct. You will get NAND OR also, just check once. NAND OR also will be degenerative, just check once. Okay, so these are the 8 degenerative forms you will get. Here if you observe, these are the dual pairs. See, and is the degenerative form. AND gate dual is OR gate, AND gate dual is OR gate. Okay, similarly here AND gate dual is OR, NAND gate dual is NOR. Next, NAND gate dual is NOR, OR gate dual is AND. Okay, next, NAND gate dual is NOR, NOR gate dual is NAND. Okay, so you can make a note. First, write all these 8 forms. Put the heading degenerative forms. Write down these 4 here and the corresponding dual here. I will give 1 point as a note. How NAND NOR is degenerative. Okay, we'll see. NAND NOR. Okay, this is NAND NOR. Okay, so here you'll get AB bar. Here you'll get CD bar. Output Y. We can write it as here it is a NOR gate. Okay, you can treat like x1, x2. Okay, x1 plus x2 whole bar. So that means here you will get y equal to AB bar plus CD bar whole bar. Now see, x plus y whole bar is nothing but what? X bar and y bar. So here you will get AB bar whole bar and CD bar whole bar by using De Morgan's law. Here 2 times complement is there, you will get AB, here CD. This one you can write it as ABCD. That means by using 4 input AND gate we can generate. So that means this is degenerative. Here in these 8 forms, whether you are having any confusion or any doubt regarding any of these forms, how it is degenerative. Okay, make a note, NOR AND. See, here I am having first stage NOR gates. That means first stage output will be A plus B whole bar, right? And another output is C plus D whole bar. First stage NOR gates I am having. Okay, NOR gate outputs A plus B whole bar, C plus D whole bar. Next, second stage I am using AND gate. AND gate means product of these two. Right? Now, consider this is like X bar, this is like Y bar. If you are having X bar and Y bar, see previously you are having X plus Y whole bar. Or you can write X1 plus X2 whole bar. Is nothing but X1 bar and X2 bar. By using De Morgan's law, X1 plus X2 whole bar is nothing but X1 bar and X2 bar. Here I am having X1 bar and X2 bar. So I can write that one as X1 plus X2 whole bar. So that means A plus B plus C plus D whole bar. So this one I can write it as A plus B plus C plus D whole bar. That means by using 4 input NOR gate, we can get this particular function. That means it is degenerative. Okay, make a note. If xy is a degenerative form, then the dual of xy is also a degenerative form. See here, degenerative form means what? We are implementing that particular function with the help of single gate, right? Either AND gate, OR gate, NAND, NOR, like that. Okay. So here, if you observe, we have mentioned AND gate dual is OR gate, NAND gate dual is NOR gate, like that, right? So here, and when you realize this one, you got ABCD. That means we can implement this one by using single 4 input AND gate. Okay. If this is degenerative form, then obviously AND gate dual is what? OR gate. So it will exist. So that means if you are having 2-level logic relation, okay, if it is a degenerative form, then obviously the corresponding dual also will exist. Will also be a degenerative form. See here you got ABCD. That means we can implement this particular function with the help of 4 input AND gate, right? Similarly, you will be having 4 input OR gate, right? 4 input AND gate dual is 4 input OR gate. Okay, here I am having NAND NOR. Okay, wherever NAND is there, replace with NOR. Wherever NOR is there, replace with NAND. Then you will get OR gate only, like that. Yeah, here I have considered for 2 input case, so that I can give the generalized case. I want to give few points, conclusions, so that's why I have considered all the gates are having 2 inputs. Okay, here X means logic gates are of X type at the first level. Similarly, Y means logic gates are of Y type at the second stage. Okay. So if xy is a degenerative form, then the dual of xy is also degenerative form. So among 16 combinations, 8 combinations are giving degenerative, right? Next one, Srp forms. AND OR relation is equal to NAND NAND. Regarding this case, we have seen we got AB and CD as the output of AND gates, okay, and we have passed through OR gate. AB plus CD we got, okay. Similarly, here also you get the same thing. Okay, if you want, okay, I will explain regarding this case. NAND NAND. That means here first stage I am getting AB bar, CD bar as the outputs of first stage NAND gates. Okay, now second stage I am using NAND gate only. So this is like X, this is like Y, XY whole bar. Is it clear? First I have considered NAND gates. First level I am having NAND gates. So AB bar, CD bar are the outputs of first stage NAND gates. Those outputs I have given as input for second stage NAND. Okay, so this is like X, Y whole bar. Now apply De Morgan's law. First term complement plus second term complement. You can say this is first term, this is second term. Okay, you are having overall complement. First term complement plus second term complement. Whenever you are having 2 times complement, you will get the normal function. So AB plus CD. So here we are having product terms sum together. Okay. Just observe here. From here I will give the conclusion. How we can implement any Boolean function with the help of NAND gates. And our logic relation, we are getting SOP form, sum of products. Okay. If you are having the Boolean function of SOP form, we can implement with the help of NAND gates. Or other way, like whenever you want to implement with any function with the help of NAND gates, okay, if you are having the function of SOP form, then you can apply 2 times complement, reverse I am telling. Suppose I am having AB plus CD, I want to realize how we can implement AB plus CD with the help of NAND gates. Okay, so whenever you are having SOP form, okay, like A plus B, OR gate, A plus B or SOP form, both are similar. Okay, you want to implement this particular function. Okay, whenever you want to implement any function with the help of NAND gates, if you are having X plus Y format or sum of products format, okay, then you can apply 2 times complement. Apply De Morgan's law for inside complement. So here you will get first term complement and second term complement and overall complement. So that means we require 3 NAND gates. Here 1 NAND gate is required. Here 1 more. Here 1 more. 3 NAND gates are required for implementing this particular AB plus CD. Okay. So you can make a note. We can implement any Boolean function which is represented in SOP form by using NAND gates. Next point you can write in other words like this. Okay. Next point. Whenever we want to implement any Boolean function by using NAND gates, okay, rearrange the given function into SOP form if possible. If we are able to bring it in SOP form, after that I will apply 2 times complement. Okay. From that we can implement easily by using NAND gates, any Boolean function. Okay. Next one, complement of SOP forms. See here we have generated SOP form. Now I am mentioning complement of it. That means here with the help of these 2 level logic relation I got SOP. After that I require complement, right? That means see here and OR is there. After that I require inverter. Okay, OR gate followed by inverter is nothing but what? NOR. So directly you can write this one is AND NOR. See I am repeating once again. Here with the help of AND OR I got SOP form. Okay, but here I require complement of it. That means after OR gate if I use inverter, then I will get complement. So OR gate followed by inverter is nothing but NOR. Okay. Similarly here NAND with the help of these 2 I am getting SOP, but I require complement of SOP. So what I will use after this state, I will use 1 inverter. Okay. So here I will get NAND. First stage is NAND only. Second stage NAND I am having. After that inverter. NAND followed by inverter is nothing but AND. So if you want you can write. See here in 2 levels I have represented like this. If you want to represent in 3 levels you can represent like this. Whatever 2 level previously you are having, the same thing I am considering. After that I require inverter and or inverter. Okay. Here I am having NAND. After that I will use NAND only, but it will act as inverter. NAND based inverter. See here I am getting SOP form and or. After that if I use inverter, then I am getting complement of SOP. Similarly here NAND is generating SOP form. After that I am using NAND based inverter. Here NAND means NAND based inverter. Like that. So that means what? If you want to implement complement of SOP form, you can use 3 stages NAND gates. Right? So we can implement the Boolean functions which are represented in complement of SOP with the help of NAND gates. See previously we have implemented any Boolean function which is represented in SOP form with the help of NAND gates. Here 2 levels. Here if you are having complement, so then I will use 3 levels NAND gate. Is it clear? Here if you observe AND OR inverter, that means if you want you can write AOI AND OR inverter. AOI. Yeah. Here last stage NAND is NAND based inverter. Here I will use, see, we want to implement all the function with the help of NAND. Suppose, okay, there I will use NAND based inverter. If you connect both the inputs as same, then that NAND will work as inverter. See, up to here I am getting SOP form. After that I want complement of it. Suppose here you are getting AB plus CD. Whatever here I am having, that will be there inside 2 level logic relation. NAND. Okay. So after that, whatever the output I am getting, okay, that one I will give as NAND based inverter. Here I want inverter, but all the gates should be NAND. That's why I am using NAND based inverter. Regarding NAND, you are clear how we are getting AB plus CD. Okay, so whatever the circuit diagram you are having, assume here. Okay, that output you pass as the same input for both the inputs of NAND gate, like that. Next one, POS forms. See here I am getting SOP form. Okay, by using these gates. Okay, if you apply dual to this one, you will get POS form. R and equal to NOR NOR. R and equal to NOR NOR. Here you will get POS form. See here you can give the conclusion from here. If you want to implement any Boolean function, we can implement with the help of NOR gates if it is represented in POS form, like that. Okay, you can make a note. We can implement any Boolean function which is represented in POS form by using NOR gates. Last one, complement of POS. Here I am getting POS, so I will use inverter, third stage. So I will get complement of POS. So R and inverter, that equal to NOR, NOR, NOR. 3 stages I will use NOR. Here R and inverter, OAI. Here AOI logic, here OAI logic. Okay, if you want to represent in 2 level, you can represent like this. First stage R gate only, and followed by inverter is nothing but NAND, equal to first stage I am having NOR, second stage NOR gate, third stage is inverter. NOR followed by inverter is nothing but OR. That's why we are calling NAND gates and NOR gates as universal gates. By using NAND gates alone, we can implement any Boolean function. Similarly, by using NOR gates alone, we can implement any Boolean function. Okay. Here I am giving the generalized how I am getting the function with the help of NAND and NOR gate. Okay. So in your exam, he may frame the question with any gates. Here we have considered AND gate, OR gate, NAND, NOR. Okay. He may frame with XOR gate, XNOR gate, 2-stage gates. Circuit diagram will be there. He will ask what is the overall output, or in order to get some output, what is the input combination? Like that he will ask. Do you have any doubts regarding these 2-level logic relations, these 16 forms, whatever we have considered? Write down the question. Identify the degenerative forms from the following 2-level logic relations. Write down the 4 choices. You no need to remember anything. See, just draw the circuit diagram, okay, and analyze what are the outputs you are getting. From that, whatever you are getting, suppose whatever the function you are getting, if you are able to implement with a single logic gate, then it is said to be degenerative. You don't need to remember anything. Yeah, option D, correct. All the above. All these are degenerative forms. Next question. In the logic circuit shown in the figure, the output Y is given by NAND. Yeah, AB plus CD, correct. Y equal to AB plus CD. In this way, you will get the questions. He will give some logic circuit diagram, 2 levels or 3 levels. He will ask what is the overall circuit output, or in order to get some particular output, either output as 1 or 0, what is the input combination, like that. Okay. Draw the circuit diagram, find out the output. He has given the circuit diagram like this, find out the output. See here, the output of this exclusive OR gate is A XOR B, right? A exclusive OR B. Here we are having NAND gate. Output Y, we can write it as A XOR B and C whole bar. Okay, here I am getting A XOR B. Here another input is C. A XOR B and C whole bar. Now apply De Morgan's law. First term complement plus second term complement. Complement of XOR is nothing but XNOR. So you can write A bar B bar plus AB plus C bar. Yeah, A XNOR B plus C bar, correct. A bar B bar plus AB plus C bar. Next question, draw the circuit diagram. See, based on the given choices, we will stop the process. In the previous question, he has given one of the choices like this. So, based on the given choices, we will do the simplification. See, here he has given the circuit diagram like this, and he is asking what is the output. See, here the output of this one is X exclusive or Y. X exclusive or Y. Okay. You can assume this is like A. This entire thing you can assume A. Okay. So that means A is coming as input for here. A is also one of the input here. Okay, now here the output of this exclusive NOR gate is what? A exclusive NOR Z. A, Z are the inputs. Output of exclusive NOR gate is A X NOR Z. Here F you can write as product of these two. F equal to A into A exclusive NOR Z. Okay, A exclusive NOR Z we can write it as A bar Z bar plus AZ. A into A bar is 0. So you will get A into AZ, that is nothing but AZ. Now you can substitute A value. A is nothing but X exclusive or Y. X exclusive or Y into Z. Okay, in the given choices he has given like this. He has expanded it. You can write this one as X bar Y plus XY bar into Z. Further multiply. So you will get X bar YZ plus XY bar Z. So based on the given choices, we'll stop the process. Okay, he has given one of the choices like this. X bar YZ plus XY bar Z. This one is exclusive OR, this one is exclusive NOR. And here you are having AND gate. Okay, last question of this particular chapter. Draw this circuit diagram. He has given the circuit diagram with exclusive NOR gates. He is asking what is the output. See here you are having exclusive NOR gates. Okay, if you are giving the normal input, suppose AB, if you are giving exclusive NOR gate, output will be AX NOR B. But here one input is normal, other input is complement, right? So when you are having like this, here output will be XOR. See here if you are giving AB are the normal inputs, then output of XNOR is XNOR, AX NOR B. But here one input is normal, other input is complement. So here we will get XOR. Similarly here also. Okay, so that means if this is 0, this will be 0, or if this is 1, this will be 1. When both the inputs are same, output of exclusive NOR gate is 1. In this way you can attempt all the questions related to two-level logic relations. One variety is, he will give the circuit, he will ask what is the output, or other variety is, in order to get a particular output, what is the input combination, like that.